Well, that's good. You can see all the live subscribers and stuff. So we should have So, yep, good to start.
Hi everyone, thank you for joining the next webinar, Data Linkage. Not sure if we can see also if many people have already joined before I start.
Yeah, we can get like live updates here. Yeah, we got some viewers, 20 or so.
Thank you for joining the Sharing Up webinar. I'm going to provide a quick introduction on who we are in BPI, what are the sharing seminars, also summary of data linkage. About BPI, the Best Practice and Impact Division is a service for all those who work with government statistics. The division brings together the Good Practice team, Quality Center, Harmonization team, Methodology Advisory Service, and also Methodology Advisory Committee. We work with statisticians and others across government to improve government statistics through advice, consultancy, training, guidance, and champion networks. BPI works to identify best practice across government, the private sector, and internationally, and shares the best practice across the GSS. What are the sharing seminars? We use themes and processes identified at innovation seminars, and the purpose of those sharing webinars is to work together and learn from each other. Today's sharing webinar is on data linkage. Data linkage is a process of joining datasets together so that we can make as much use as possible of the information that they hold. While datasets are useful on their own, bringing them together effectively means that we can take advantage of the combined research that they offer, giving us new insights into the data subjects with them, answering society's questions, and driving policy change. We have two speakers today for this webinar. We have Clara Boyd joining us from Ordnance Survey, and she's going to show us the work done towards the Geo6 Data Discoverability project, where they maximize the value in their geospatial data by matching together different data to produce catalogs of all the data they hold. We'll then hand over to Robin Lineker to talk about the Ministry of Justice newly developed software called Splink, which is a probabilistic data linkage tool running on Python in Apache Spark. After each session, we're gonna spend a few minutes on questions. You can send your questions via Slido. The code is G727. You can see this also on the slides, or you can also comment on the video feed. Please, in the meantime, if there are any technical issues, just let us know. I'm going to hand over to Clara now.
Hi, my name is Clara Boyd. I am the Data Standards Manager for the Ordnance Survey. I've been involved with a project that we call Data Discoverability for nearly the last year. And so much has come out of this project. One of the things being we did a lot of thematic matching, which should help on the journey to data linkage. So what was the problem? Well, we found that actually we had we had an incomplete picture of geospatial data held across government. We didn't have enough information about it. We didn't know what was held, and it led to a lot of missed opportunities. It meant that we didn't expand on potential of unlocking this data. And actually this project, we're hoping, will enable people to find and use data and open up a lot of economic growth. So what is the Geo6? Well, the Geospatial Commission was formed out of the autumn budget in 2017, and we have 6 geospatial organisations that report to the Geospatial Commission, and we call them the Geo6. These 6 organisations have a variety of different types of geospatial data, and we've been working together on a variety of projects since the Geospatial Commission has been formed. This is just one, and there are quite a few others, which including actual data linkage project, which is very highly linked to this one. So the Geo6 data. Well, what we found is actually a lot of the Geo6 geospatial data falls into 4 very broad categories. Apologies, I've also realised that legal doesn't have they're not lined up the same as my slides. So the Geo6 actually hold altogether about 2,600 different data sets across these 4 very, very broad categories. We all have our own domains. We also cross over largely in different areas. And we found these were very, very broad, and we needed to be more specific and what is going to be useful to our users and actually finding data. So what we started to do is we had a workshop where we looked at how do we actually group this data together? How do we get this data and all these data sets into a formation that is useful to our users? Well, what we started doing is actually creating themes and categories that we thought our data fell into as the Geo6. But what were these things that they fell into? And what were the overlaps that came with them? Well, what we actually found is that they overlapped heavily with Inspire themes from the European Commission initiative, which was really helpful for us because not only did that come with its benefits of it being from a controlled vocabulary, which meant that people in the industry would be able to identify what broad theme these data sets fall into, but also gave us a mechanism to start thematically matching all of our data sets to these themes. So what did we find? Well, first off, the main thing we found is that we have a lot of data that falls into many, many themes. It allowed us to see where we've got many data sets. It also allowed us to see where we have relatively large gaps between the Geo6. And one thing that we found really interesting is actually how different the Geo6 organisations are. We have multiple agencies with data falling in the same themes, which is, I guess, very good, but is also actually where do these overlap and is that an issue? So this led to lots of questions about the data sets in the individual themes. So for example, what do people call their data sets? Are they overlapping? Are they the same? So for example, the Coal Authority has a data set called mine entries, and Ordnance Survey have a data set called adits. Well, actually, they are very overlapping. They are essentially the same thing. But what about the coverage? Well, we all mostly look at Britain, but actually we'll have smaller data sets that will only cover particular areas, and where do they overlap? Also, how update is the data that we're collecting depending on the organisation? What is the data? What is the purpose of the data? What is the reason it's being captured? What is the use case around that? We're looking at specifications. So how is it actually captured and how do you maintain the data? Also, are we using controlled vocabularies? Are we using uncontrolled vocabularies? And also, do the data sets we're looking at actually match exactly, or do they just complement each other? So there's lots of questions that came out of our initial matching exercise. So what happened is Inspire also has feature types and feature catalogues, which is a more granular level than Inspire theme. And we thought actually this might give us some more information of overlaps and how we can work out best data sets to use when you're discovering new data. So again, we had to do a thematic matching exercise where we take our data sets and instead of applying them to the theme, we apply them to the feature type. And again, that was experts coming together and working out where they all fit. So what's the benefit of this? So I've got two examples here. The first one is about Mansfield sample data. So if we start layering up some geospatial information, so if we start with looking at the Mansfield area and a small geographical area within that, so if we start building that up, if we start with British National Grid, we can start adding data layers. And what you'll see is actually many of these fall into different Inspire themes and different feature types, but give you a lot of information, and all this information generally complements each other. And that you can add all these things like aerial imagery, you can add all of your energy resources, your mineral resources, and it gives you a fantastic picture of geospatial information in Mansfield and how it all fits together. So there's large amounts of data and they vary dramatically by themes, but they complement each other very well. And that's because the only overlap we have here is actually they're the same geographic location. But if we look at a different scenario where this isn't the case, we've got an area of cows on the Isle of Wight. Here we go. So this is OS data, aerial imagery data. And if we start overlaying different data sets, so here we can start with the OS mean low water. And as we build these up, you've then got the OS mean high water. So although they're in the same Inspire theme, they're in different feature types. But then we've got the UKHO data, which is also intertidal area. And very closely, if I flick back, lines up to OS. But actually, they're very, very slightly different. Going further, we then have HMLR's national polygon data set, which shows ownership. And that falls into, again, a different Inspire feature type. But their boundaries, again, are very similar to your OS mean high water and your UKHO electronic nautical charts. And if you add another one, which is very hard to see, I appreciate, of intertidal vegetation, again, there's another overlap. So what does this mean? Well, actually, we've got a variety of information that we don't know which one is the right one to use in what scenario that you want to use it for. So it's all very well, we've done this matching exercise, which is extremely useful, is extremely helpful in finding data and discovering data, but how can we go further than this and actually help people within that work out what data that they want to use and is appropriate for them? So that leads to the second project in the data discoverability, and this was split into 6 work streams, but for this presentation I will just be focusing on the 4 most relevant for this area of work. So the first one is data granularity. We've also looked into search engine optimization, portals, but also authoritative data. Each of these is focusing on how to make data more discoverable and informative to the user, and it's something that we think that will complement our matching exercise to make what we present on the web when looking for data even more valuable. So first off, granularity. So this is really looking at how granular do we present our data sets at. So if you're looking at, for example, geology data, would you present data sets at geology, or would you set them at a type of rock, so sedimentary rock, or would you go even more specific to a really specific type of rock? Well, actually, we did lots of research into what is the optimal point to make data most discoverable on the web based on how people actually search. So we did a lot of user research into this, and what we found is people do want a level that is what we call in SEO terms chunky middle. And this is something that's not so specific that hardly any people ever search for it on the internet, but not something so broad that you're searching for geology. We think that actually this helps us strengthen the link between datasets and Inspire themes, because although Inspire themes are great for people that know the vocabulary and understand the context, it's not necessarily the best for people that are trying to discover data they haven't ever found before. So what we've tried to do is also find the best terminology for everything we do, and it takes us past the themes to something that we can understand more when discovering data. So instead of using, say, OS uses the term roof structures, we'll use the term buildings. So what was the SEO and portal section? So the SEO was looking at a variety of things to make data more accessible on the web when you're searching, say, on Google, which is obviously the most used search engine. What we found is actually using keywords, so your Inspire theme, your Inspire feature type, even UNGGIM themes. They are fundamental in understanding whether the data is right for you, but also getting you to the right data when you're searching. There are very, very specific ways how to use them, depending on what platform and portal you're using, but they are an essential way to get to data. And optimize for Google, that is what most 80-90% of your users are using. What is the importance of portals in this? Well, actually, we gathered information about what users want from a portal. So they want information up front. They want to understand whether the data set is right for them, which is essential when we were matching, is that we get that right. And information users look for to assess usability of the data sets. Again, it is a fundamental thing, especially if you're potentially looking to link the data together. So a really interesting one is we actually looked at authoritativeness and authoritative data. Well, our main outcome for this is we came up with a process that allows us to assess, firstly, is an organisation, what is their trustworthiness? So government is a key one, which most people on the outside will assume government data is very trustworthy. They're a trustworthy organisation. We also look at the quality of the data set. Is the data set of good quality on a scale? But also, one of the things that will be essential for linkage from users wanting to do that is that potential future work could include assessing user cases against quality, which is obviously fundamental in understanding whether that is the right data for you. And hopefully that will have a knock-on effect to the other work streams within that project. So what does this mean? Well, actually, one of the things that we want to do is by making informed decisions through starting the matching through thematic of themes. This allows us to give power back to users when making decisions on what they want to do with data, whether it is layering data and using complementary data, or really going into the specifics of linking them together. We want to give users the power to understand that, have the information up front that they need to make those decisions, and give them the best possible chance to get the best possible outcome. So thank you. If anyone's got any questions.
Thank you, Clara. I guess we'll have to wait a little bit because there is a deadline.
That's fine.
Any questions? Just send us on Slido or on YouTube channel.
No?
question. Maybe we can move on to the next presentation, and if there's any question, we can gather the questions in the end.
Just quickly to add, the main outcome of this project is a list of data catalogues on data.gov.uk, where you can see all the work that we've done, and including things like matching all of our matching exercises.
Okay, thank you.
Just going to make sure these are going.
Yes, it's that first step there.
Just need to bring it to the other screen. Cool. Sorry, it's just the screens are in a funny order. Cool. Hi everyone, my name is Robin Lineker, and I work at the Ministry of Justice, and I'm going to talk about Splink, which is a piece of software for probabilistic record linkage at scale. This is work that I've been doing with my team at the Ministry of Justice, so that's with Sam Lindsay and Theodore Manassis. So just to give you an outline of what we're going to be talking about today, I'm just going to briefly describe the business problem that we're trying to solve. I'm going to talk a little bit about the technical challenges we've run into, tell you a little bit about why we decided to build a new software product rather than use an existing one. I'm going to do a little bit of a demo of the software, hopefully that'll work, and then we'll talk through a few conclusions. So in terms of the business problem that we're trying to solve with this software, like many government departments, the Ministry of Justice has got many different large-scale sources of administrative data. These are typically computer systems that were built independently, so there's often no single unique identifier that exists to identify, let's say, people or other entities within those records. And what we believe is that improving the quality of our data linking will underpin improved insights into the effectiveness of justice system interventions and repeat service users, amongst various other analytical uses. So moving on to the technical challenges, one of the biggest technical challenges we face is that across these data sets there are tens of millions of records, so it's a very big data linking problem. And our data sources typically need to be both deduplicated and linked, so it's not even that the individual data sources are necessarily deduplicated when you go into the linking. There's also, like, generally, not just at the Ministry of Justice, it's hard to find large scale and realistic training data sets, so like labeled data sets for kind of training models. And another challenge is because we've got such a number of different input data sets, which are quite different in their characteristics. We need quite a flexible solution to data linking. So not something that is kind of bespoke, works for 2 data sets, but then doesn't extend to the 3rd, 4th, 5th, etc. And finally, one of the technical challenges we're going to face, and we'll talk about this in a bit, is the problem of transitive linking, resolving the graph. So what I mean by that is if you link record A to B and B to C, then that sort of implies that A links to C, but that whole issue can get quite complicated. So I want to, just before we do the demo, I want just to talk a little bit about why we decided to build a new software package. So we're still a fairly new team who are set up to kind of modernize the approach to record linkage that we use. And what we started by doing is doing a literature review, kind of reading relevant books, looking at kind of videos of people talking about data linking on YouTube, and doing a review of the open source software which is out there on data linking. And this kind of process of doing this kind of research, we found a number of things. So the first thing we found is that we couldn't find any existing open source software which worked at the necessary scale. So we found quite a lot of good record linking packages, both in R and Python and in other languages, but none of them seemed to scale up to the sort of tens of millions of records we needed it to. Our sense after trying some of these packages is that the FastLink package in R is probably the best current implementation, although there are other good implementations too. And that is great, except that it probably scales up to sort of tens of thousands of records, possibly 100,000, but definitely not records in the millions. Another finding of the review is that there's a statistical model called the Foleggi-Sunter model that can be estimated using an expectation maximization algorithm. This is talked about quite a lot, and we think that it offers a good balance of transparency and performance. So by that, I mean there are probably some more sophisticated sort of machine learning techniques if you have training sets that might give you slightly more accurate matching, but they might suffer in the form of like transparency and being able to explain why a match has occurred. So Foleggi-Sunter, we think, probably gets you fairly close in terms of accuracy, and also is quite easy to explain what's going on. So we think that that's a good balance. And just as we were doing this review, one of our observations and one of the things that led us down the route of building new software is that if you look at the Foleggi-Sunter model and the expectation maximization methodology, it turns out that it's almost trivially parallelizable, which means it's very suited to distributed computing frameworks like Apache Spark. So what I mean by that is that you can take a big computational problem, you can split it across multiple computers, and those computers can work basically independently without having to talk too much to each other, which means that by adding more computers to the cluster, you can speed up your runtimes. So what are our aims of in building this new piece of software? As I've sort of mentioned, we want it to work at much greater scale than current open source implementations. So we're aiming for it to work at 100 million records plus. We want it to get results faster than current open source implementations. So we're aiming for runtimes of less than an hour, even for large record linkage problems. And we want to have a highly transparent methodology, so that match scores that come out of the algorithm can be easily explained using both graphics and words. We're hoping that we will have accuracy similar to some of the best alternatives, whether they be open source or commercial products. We want to make sure that our link data users are given access to link confidence, so like the scored confidence in each match, so that they can perform sensitivity analysis on any onward research they do. And we want to make sure that the package has considerable flexibility and customizability. So that is to say, we want to make sure that it can tackle the majority of record linkage and data deduplication problems. And finally, something really important to us is making sure the package is really robust, which is to say it's got a very high standard of quality assurance, including an automated suite of quality assurance tests. So we're going to move on to a demo of the package. So the package is completely free and open source, and anybody watching this, you can go to the URL there and you can run an interactive demo of the software. Again, it's a really tiny server that you'll get, so it'll be quite slow, but you'll be able to see what's going on. So I'm just going to show that here now. So this is the main homepage of Splink, and if you kind of scroll down, you can see there's an interactive demo here which says launch the binder. So this is just GitHub MOJ Analytical Services Splink, and we can have a look at the interactive demo here. So when you go into it, you can look at various demos, deduplication, linking and deduplication, and a bit more about configuration and settings. So we're just going to have a look at the data deduplication quick start demo, and I'm just going to kind of talk through how it works. So in this demo, we're going to deduplicate a small data set, and the purpose is to provide an end-to-end example of how to use the Splink package. In step one, what we're going to do is just going to configure everything. So those of you who have used Spark know that you kind of need just to give it some configuration options. I'm not going to talk now in any detail about what those are doing. But once the Spark environment is available, in this demo, we're just going to show you the data set that we're using. So this is a synthetic data set that was just kind of randomly generated by me. But we can see here that what we have is a data set of 1,000 rows. There are sort of groups of records, and because I created this data set, we actually have labeled data. So we can see that these first 4 records are all the same person, but there are various perturbations, like there are errors in the date of birth, there are some nulls, there are some typos that we can see here. And then the data set moves on to a second group, truncated at 5 records, but there's various Noah Watsons coming up. So that's the data that we're aiming to deduplicate here. And in order to use the software, the main thing we need to do is sort of configure it. So tell it what comparisons need to be made and how to run. And the way we do that is using this settings object, which is a little bit complicated, but we offer various tools to make it simpler to write these things. So just to read through what this is saying, we're saying the link type that we want to use is we want to deduplicate this data set. The other options are link and deduplicate or link only, but here we're just deduplicating. We're going to give it a bunch of blocking rules. So those of you familiar with kind of data linking theory know that to make these problems computationally tractable, we usually need to use blocking rules. The blocking rules we're going to use here is that we're going to only look for comparisons where either the first name matches, the surname matches, or the date of birth matches. And these can be arbitrarily complex. So you can say first name and surname, or any kind of combinations you can think of. They're just SQL expressions, actually. So those are the blocking rules which are going to generate record comparisons. Once we have those record comparisons, we then need to configure what columns Splink is going to use to compare to generate match probability scores. So here we're going to compare on first name, surname, date of birth, city, and email. So that's all of the different fields we have. And we're going to give a bit of additional configuration options for the first name and surname columns. So one of the things we're going to do is allow more levels to the comparison vector. So that's a bit technical, but what that means in practice is that Splink, the software, is going to be able to distinguish between an exact match, so Julia versus Julia, a kind of fuzzy string match, so an almost match, so that could be a typo, and no match at all. So if we look at the data above, this email would be that kind of middle fuzzy layer if we were doing 3 levels on the email. We're going to do the same with surname, so we're going to allow that kind of degree of fuzziness. And the other thing we're going to do with first name and surname is we're going to allow the software to make term frequency adjustments. So what that means is if you're doing record linkage and you link somebody called John to somebody called John, that probably doesn't give you a high degree of confidence they're the same person because John is such a common forename. But a forename, let's say Robin, is a bit less common, so you would expect to have a bit more confidence if you linked Robin to Robin. So that just means that because we know that the first and surname columns have this kind of, they have quite high cardinality, but the kind of distributions within the specific names are different. It allows us to account for that. So that's the settings dictionary. As I say, it's a little bit complicated. So what we do is we provide an autocomplete editor here. And what this does is it kind of allows you to kind of write a settings dictionary. And as you write it, it will automatically validate it and tell you what errors are going on. So here you can see I've put high in num levels. And at the bottom it's saying that we expect an integer at line 7. So if I switch that for 2, it now is that error has gone. The other thing that's really helpful here is that if you just mouse over stuff, it tells you what the settings do. So hopefully this should help people a lot in just writing these settings dictionaries. So at the moment it's telling us that everything's fine except we're missing a link property, the link type property. So we can add that in. At the moment it doesn't know whether it's a. So we can see we've got autocomplete here. So it's saying we want link type, so we're going to autocomplete that. And then I think even this will say that there are 3 options for link type. So we could put dedupe only. And now we have a valid settings dictionary. So hopefully this helps people quite a lot in kind of authoring these things. So just moving on, so we've set everything up. So actually doing the linkage is then really simple. You just import Splink after installing it. So it's just a standard Python package that uses Spark, but it is just a Python package. You then have to give Splink the settings that we just configured. You have to give it Spark so it knows where to execute everything, and you have to give it the input data frame that we loaded in. And then you just ask it to give you back the scored comparisons. And what we see here now is it's running the expectation maximization algorithm. In this case, it's running 10 iterations, but you can configure that. And once you've got that DF comparisons, we can then just kind of inspect it and see what's going on. So just looking at the first few comparisons, what Splink tries to do is it tries to give you outputs where the columns are organized in a way that are quite easy to understand. So like it's setting, in this comparison, we're comparing record row number 0 with row number 1, which are both this Julia person. So we can see that we're comparing first name Julia to first name Julia. Surname, well, in record 2, there was a null, I think, in the surname. So we're comparing null to Taylor. The date of births don't match, but if we carry on along, if I can make the mouse work, we find that the city and email do match. And so we end up with a match probability of 0.99. And the results, if we look through all of this, are not too bad. But what we generally find is that for smaller data sets, like input of 1,000 records, basically like the iterative algorithm doesn't quite have a chance to get enough information about enough comparisons. So the more data you give it, the better results you get. Okay. So I talked about like the transparency of the algorithm before and why it's really important to us that we can explain the results coming out. So although we get a kind of match probability out here, like this data frame doesn't really quite explain how we got to that score. So we offer quite a few graphical outputs from SparkLink that will try and explain this. So I don't have time today to talk about the kind of Foleggi-Sunter theory, but essentially it comes down to looking at frequency or probability distributions among records which are matches and comparing that to records which are non-matches. So if we find that, let's say, the first name tends to match amongst records which are true matches and tends to not match amongst records which are not true matches, then if you observe a match on first name, that gives you quite a bit of information to indicate that it's a match. So that's what these frequency distributions are doing. On the left-hand side, we've got the distribution amongst records that Splink thinks is a non-match, and on the right-hand side, we've got probability distributions amongst records that SparkLink thinks is a match. This can be a little bit hard to read, so we have a second representation down here. And this one is more like giving you the kind of weight of evidence representation. So if we look at date of birth here, what this is saying is level 0 corresponds to no match. So where date of birth does not match, what this chart is saying is that gives us quite a lot of information to suggest that the comparison is not a match. And you can think about that in the sort of Bayesian sense of, you know, if you have a prior and you find that date of birth does not match, this is how much you update your prior. Similarly, if date of birth does match, we can see that this bar is pulling quite up, pulling upwards in a positive direction. So what that's saying is if within a comparison date of birth matches, that's quite strong additional evidence that we have a match. Email here we can see is even stronger evidence, and that's because within these data sets, email has really high cardinality. So it's actually acting quite like almost like a unique identifier. You can write all that out to an HTML file, and that'll actually give you a few additional charts, which will show things like the iteration history. So when you're using an iterative algorithm, you want to know usually whether the iterations have converged, and that'll come out in this file, which will just output to it like a dashboard. The last thing I want to talk about is the intuition report. So what you can do here is you can pull out any individual comparison from your data frame of comparisons like this one, and you can get Splink to explain what's going on and why you got the score. So I won't read through this whole thing, but basically what's going to happen is Splink is going to estimate the probability of a comparison taken at random being a match. So that's basically, if you take a comparison to match, this is kind of like your prior of how likely that comparison is to match. So in this case, that's 0.41, so 41%. And then this report is going to say, okay, so that's our prior for any random record, but now we're going to compare the first name field. And the value of the left-hand side record is car for first name, and the value of the first name on the right-hand side is brown. So something weird is going on in this record. And what it's going to say is it's going to give you a Bayesian adjustment factor, and it's going to say, well, first name doesn't match. And so this probability is less than 50%, so that's evidence against it being a match. And so that 41% we started on has come down to 33%. It's only going to compare surname. We've got Ethan and Ethan here. So what we have a lot in this data set is inversion of first and surname, so that's why we have some weird stuff going on here. So what it then says is that actually in this case, we have quite a bizarre outcome where Ethan versus Ethan actually results in a downward adjustment. That's actually a product of the blocking rules. If you only pick records where surname matches, then you can sometimes get slightly perverse outcomes here. But in any case, what this intuition report is telling us is that has actually brought down our match probability to 28%. And then it's going to get brought down quite a lot further by a non-match on date of birth. That has a very strong downward adjustment. The other adjustments we've made so far have been quite small. So we're now down to 5% after taking account of date of birth. Similarly, city and email don't match. And once we take account of both of those, our final belief is that it's a 0.2% chance of a match. But what this means is once you've estimated your model, you can get a sense of whether you think it's doing something sensible. So in this example, for instance, this Ethan comparison, where even though the surname matches, it's actually reducing our belief in probability. This is the kind of thing that would flag up and say, well, maybe there's something not quite wrong. Maybe we didn't run enough iterations or something like that. But anyway, it helps explain what's going on. Finally, step 7, we didn't actually make term frequency adjustments before, and that's just because in practice we found that if you try and bundle that in with the main iteration calculation, when you're having, let's say, hundreds of millions of record comparisons in really big jobs, Spark has a tendency to blow up. So we've just split this out into a second procedure you can run, linker.make term frequency adjustments. And if you do that, you get the same data frame out, but you have a second column called term frequency adjusted match probability. And you even get some information in there about the size of the adjustments for term frequencies. So where that's 0.5, that just means no adjustment has been made, and that tends to be the case when the first names don't match anyway. If the first names don't match, there's no reason to make a term frequency adjustment. But if we go down to, let's say, this record, we can see that the adjustment factor is 0.36. We can see that the first name there is Jack, and that makes intuitive sense because Jack's quite a common first name. So that means that we're sort of reducing the amount of confidence we have. Even though Jack matches Jack, we're saying, yeah, but actually there's a lot of Jacks, so maybe we're not quite as confident as we thought we were. Okay, I'll switch back to the slides now, but I'm almost done. Cool, so that's the demo. So I encourage people just to try it out for themselves. These are just some backup slides in case all of that broke. That's just a picture of the dashboard with the iteration history that you get out. So last two things I want to talk about are kind of collaboration on this. So first of all, I'd just like to say we're really indebted to ONS, in particular Rachel Shipsey's methodology team, for just their insights they've been using for Leggy Center for quite a while, and they've been giving us methodological advice, and they're also going to be helping us out with a little bit of QA on this. So we're really happy about that. The other thing that we're really pleased about is we're working with a leading kind of data linking academic in a kind of advisory capacity on this. So that's just helping increase our kind of confidence that what we're doing here is sensible, is giving sensible results, that sort of thing. Next thing I'd just like to kind of emphasize again is that Splink is 100% open source. Everything you've seen you can just download onto your computer and use. And we've even got those interactive demos to allow you to play with it without having to like install Spark or anything. We'd be really grateful if people could give it a go, tell us about any problems that they have with it. You can raise an issue on GitHub to let us know about problems, or just email us directly. And actually, like, one of the observations I have looking at kind of data linking in government is that like seemingly every government department we talk to needs to do data linking in some way, and everyone's got kind of a different solution. And what we'd really like to do is collaborate. If others would like to get involved in the development of this software, that'd be great. Or just you want to try it out and you want some advice on how it works, whether it's a bug report, contribution, documentation, or anything like that, that would be fantastic. And our kind of lofty ambition, but it would be wonderful if this happened, is for this kind of software to become a standard package that's used often in government for doing data linking. Obviously, that's only possible if other people try it out and help out. So just concluding, thinking about our further work with this. So we've got to the point where we can do scored kind of record comparisons, and at the moment we use something called connected components to resolve the kind of graph of those comparisons into groups. So what I mean by that is this thing where if you've got your record matching scores tell you that record A matches record B and record B matches record C, then you need an additional bit of computation to tell you that, well, A must be in the same group as C. So A, B, and C all form a group, and we want to give that group like ID, group ID 1. The connected components algorithm is relatively unsophisticated, and we think that there are more sophisticated graph algorithms that can improve the link quality. And in particular, that's things where you kind of want to prevent like all John Smiths in your data set all becoming one massive group. And connected components can sometimes cause that to happen if you just have one strange John Smith who happens to link to everyone else. The next thing is that we're working on improved mechanisms for linking where multiple records exist for each entity. So if you have like somebody's address history or something like that, how do you take account of the fact that you actually have several addresses for them, not one? Also like name aliases. The next thing is that you've seen kind of the interactive demos, and at the moment, like, so we've got doc strings within the code and we've got those demos, but we don't have like a full suite of documentation to explain how this works. So we want to do a bit of work on that. And then the last thing is that Flegi Center obviously gives you those nice linking scores, but there are various other ways of computing scores, either using string comparison functions, which we've done quite a bit of work on, or possibly using machine learning. And there's really no reason not to combine these different sources of information. So we're possibly looking at the moment about whether we can sort of increase the accuracy of the Flegi Center scores a bit using machine learning. And that's it. Thank you all for listening.
Thank you, Robin. I can see on the slide that there are a few questions for you.
Great.
So the first question is, how does Splink deal with missing values? Does it avoid giving misleading links where it has joined missing to missing?
Yeah, good question. So hopefully we can see that actually here in the intuition report. Basically, the answer is that it does. So in this intuition report, we were seeing that each time we made a comparison, we could sort of update. So we had our initial prior, we gain new information from each comparison, and we update our new updated belief of match. Where one side of this comparison is a null, you simply don't update the belief, because you would be comparing car to null, and you just in that case you just have no information, because null is not a blank string. It's not no information. It's just we don't know. So you simply don't update the value. That's actually really important, and I imagine that the person who asked the question realizes this. In the case where you're linking, let's say you're linking three data sets where two of them have common columns, but that column is missing in the third data set. Where you have that, you don't want to just have to delete that column that is present in two of your data sets but not in the third and not use it for linking. What you want to do is include it and just null it out in the third data set. And what that does is it allows Splink to get information from that column where it exists, but where it doesn't exist, treat it correctly.
Next question is, when you were looking at other open source legend software, did you look at BigMats from the US Census? Do you find particular downsides to BigMats?
That's not actually one we've looked at, so thank you very much for that suggestion. We will take that away and have a look.
Thank you. Next question is, can you explain how the algorithm deals with comparisons across variables, for example, surname versus forename, when they're swapped?
Yeah, so that isn't something I talked about in that simple demo, but basically, if you're configuring the settings object, the simplest thing is just to do a comparison on first name, but there's something called a custom case expression you can use, and that allows you to do a comparison with something like a first name surname inversion. It basically allows you to make a comparison using an arbitrary SQL expression of your choosing. So that means that you can make it whatever you want.
Next question. There are many questions for you. How do we can advise about setting up distributed computing?
Yeah, so like if you want to know a bit more about this, we're probably going to include in that demo repo an example of this. But at the Ministry of Justice, we use in Amazon Web Services, there's a service called AWS Glue that basically means that you don't have to manage your own Spark cluster. And we've got on really well with this. So when we started working with kind of big data technology, the thing that we found really quickly is that we were only going to use it if we didn't have to manage the infrastructure, because it's really complicated and quite expensive to manage. Each cloud provider, as far as I understand, has got a kind of managed Spark cluster as a service. So this isn't just an AWS thing. But if you want to get up and running quickly, it will be much easier and cheaper if that kind of fits in your departmental security advice and all that sort of stuff. But yeah, we use AWS Glue. That essentially means that we can just send a Spark job to AWS, and they then take care of spinning up a cluster and running everything and giving us back the results. We've got a separate open source package called ETL Manager, which was developed by a colleague of mine called Kara Kasice, and that dramatically simplifies that step of taking something like SparkLink and basically telling AWS all the information they need to run it. It reduces that to like 2 or 3 lines of code.
Nice, thank you. You described Splink as a tool for linking very large datasets. What size of datasets for linkage make it worth taking this approach?
Yeah, so if you've got a Spark cluster already, you can do it on any size. So there's a paper which accompanies the R package called FastLink, and it's got a really good chart where they compare the speed of execution of different open source packages, including their own. And basically, if you look at that, you see that once you get to something like 30 or 40,000 records, they're showing runtimes of like 10 hours plus, and it's going up exponentially. So what I would suggest is if you're doing kind of deduping, linking on kind of over tens of thousands of records, then you're going to probably run into problems in R reasonably quickly if you're using that package. In terms of our runtimes, we're seeing runtimes of about 30 minutes to do a dedupe of 16 million records. So this is going like quite considerably faster. Incidentally, that FastLink package, it's really good, and actually what Splink does is it actually kind of just implements a lot of their logic and their model. So what we've really done is we've looked at FastLink, we liked it, and we've rewritten it so that it runs the computations in Spark, but other than that, it's actually quite similar.
Next question is, did locally sensitive hashing and use of Jagged similarity to generate first get tried evaluated?
Yeah, that's a really good question. We spent ages trying to use LSH, locally sensitive hashing, and so basically we did a grid search of like basically LSH. I won't go into the theory here because it'll take too long. But basically, there's a lot of different settings and parameters you can choose for LSH, which might be relevant to different situations. What we found is that for large data linking problems, it doesn't like reduce the comparison space enough. And we did a kind of grid search of parameters to see if we could find settings which would reduce the number of comparisons. But it's this Cartesian product thing, right? If you've got 1 million rows and you're trying to do 1 million versus 1 million comparisons, then that's just not computationally feasible. So LSH would be great if you could find some LSH settings that turned each row into a nice hash, and those hashes had fairly high cardinality that in turn meant that you didn't need to do 1 million versus 1 million anymore, and maybe you reduced it to like 100 million comparisons in total. We couldn't find. So basically, what we found is that we could find some settings that reduced the comparison space quite a lot. But what they also did is meant that you lost a lot of valid matches. So we just couldn't find some settings that worked. If anybody else has found settings that worked, we'd be super interested in that, because we think that potentially, at least, it's a really good approach. The other thing was Jacquard similarity. So you can use Jacquard similarity and a bunch of other string comparison functions actually within Splink. So one of the pieces of work that Theodore Manassas did as part of this project is he took a whole bunch of some of the most widely recommended string comparative functions within the data linking literature, and he's written them, or there are Scala implementations that he's developed. Mostly ones which are open source already, but he's kind of translated them to make them available within Spark. So if you're doing record linkage and you don't care about Verlegi Center, but you do care about string comparison functions, I definitely take a look at that, because they're now native Spark functions, which means that they run a lot faster in Spark than if you're using, like, let's say, a Python user-defined function.
When you change number of levels for name variables, what is the algorithm changing to make the matching fuzzier? Is it string comparison measures?
String comparison measures, yeah, that's right. So basically, Splink has got a whole bunch of sensible defaults that run inside it. But really, what's happening when you're saying that there are 3 levels, if it's a character like a string variable, it will pick a SQL select case statement. And for the 3-level case, that'll be a select case statement that says, if the Jarrow-Winkler comparison between the two things is greater than, I think it's 0.94, then assign it similarity score 2, so the most highest similarity. If Jarrow-Winkler is above, I think it's 0.88, assign it similarity 1, which is like the middle version. And if the Jarrow-Winkler score is below 0.88, then assign it 0, which is basically to say that they're not similar. Those thresholds are taken from the R FastLink paper. It's what they recommend there. But again, you can always write your own custom select case statements, which means that you can either change those thresholds if you want. You can use different string comparisons if you want. It's kind of up to you. So all that's going on there is, if you don't give it a custom case expression, it'll pick a fairly sensible starting one for you. Within Splink, there's also a library of these things. So if you want to use one of our kind of defaults but adjust it a bit, there's various ways of doing that actually within the software. And there's also numerical comparison functions which do a similar thing if the column you're comparing is numerical rather than string.
One more question. Felicity Center scores are relative likelihoods. How do you convert these to linkage probability?
Yeah, so I would probably direct the person to the R FastLink paper, where they what's really great about that package is not only is it a nice open source R package, but they actually published a academic paper in like a real peer review journal that explains the methodology. And the methodology that we're using is exactly the same as that. So I would suggest looking at that. But essentially, the answer to the question is, if you look at the intuition report, that's pretty much how you're getting the probability values out.
Thank you. Thank you, everyone, for all these questions.
I've lost the mouse.
I'd like to know that all these material from today's sharing webinar, we're going to upload all the slides and the contact details on our website on GSS sharing webinars. The next sharing webinar is going to be on June around uncertainty. So if you have any suggestions around that, you can email us on GSS.Health.Statistics.Gov.UK. We want to apologize because a few departments couldn't access today's sharing webinar, but this is because they couldn't have access from their work devices on YouTube channels. In this case, we recommend that you can watch the webinar on your personal devices, and we're really happy to get any questions on GSS Help, and we can follow up with you. once you watch these webinars. You can also join us on Slack. And that's it from us. Thank you, Clara and Robin, for joining us today. And we all hope you enjoyed today's webinar. Thank you.